Kia ora, good afternoon to my physicists. Today is the 6th of May, Haratua is May 2020. A couple of fellas have had a spot of bother with question 4 on page 11 of the workbook, and they wanted me to give them a hand with it. I thought that's a good idea. So let's have a look at it. I've taken a picture and dropped the picture in here. So page 11, question 4, waves of frequency 60 Hertz. Pass from deep water, boundary from deep water, speed 3.5 meters per second, into shallow water, speed 1.5 meters per second. You need to calculate the wavelength in each region, and I'll do that first. So first of all, in deep water, now the frequency does not change. If the waves are coming in 60 waves a second, well, they'll keep coming at 60 waves a second. Where it goes fast, they'll spread out like cars on an open road, and where they go slow, they'll jam up. That's what changes the wavelength. So we know that V equals F lambda, and I'm going to swap sides. So V equals F lambda, so V is equal to F lambda, and then I'm going to forget this bit. Then I want to make it so wavelength is a subject of the formula. It's cluttered up by being multiplied by F, so I divide it by F, and I divide both sides by F because the equal sign means this side is the same as that. If I change this, I change that. The F's on the left cancel. And then I can have the wavelength is, then I put the numbers in. V is 3.5, F is 60. Now if this was 3, that'll be 1/20th. If this was 4, it'll be 1/15th. So this will be somewhere between that. So it'll be slightly more than 1/20th of a meter, which is a bit more than 50. So that's going to be 0.058 millimeters. Now what I'm going to do here looks a bit odd. I'm going to copy, paste, and then chop out the things that I don't want. So moving along, in shallow water, the frequency is still 60. The velocity is 1.5. We need to find the wavelength. Same sort of situation again. The wavelength is equal to the speed divided by the frequency. 1.5 divided by 60. Well, that's 1/40th, and that's going to be 25 millimeters, or 0.025 meters. 1/40th of a millimeter, 0.025 meters. That's cool. That's the end of the wavelength part. Now let's look at the refraction. This is a bit trickier. There's a few little fishhooks in this question. If you zipped over it, you probably missed a couple of those. In the shallow stuff, because it's refracted, coming from the deep to the shallow, so it's refracted to become 20 degrees. We need to find the deep angle of incidence. So from page 9, there's a formula there. Sine theta 1 over sine theta 2 is V1 over V2. And I'm going to set 1 as the deep, where the speed is 3.5, and set the shallow as number 2, which is 1.5. So what I'm going to do here is put in these formulae that apply. Sine theta deep over sine theta shallow, V deep, V shallow. And then I'm going to, I really want to have theta deep all by itself. So I'm going to have sine theta deep by itself first. It's currently divided by the sine of theta shallow. Multiply both sides by the sine of theta shallow to get rid of the thing cluttering on the left-hand side. And then the left-hand ones, the sine of an angle is a number. This is all one number, so they can be cancelled. Sine of theta deep equals now this over here, I just copied and pasted it down, or rewritten it rather. And then I want to find not the sine of the angle, I want to find the angle. Now to find the angle from the sine, you find the inverse sine of it. The inverse sine of the sine is just the angle. Now if I have found the inverse sine of the left, I have to find the inverse sine of the right. So I've done that. And I write that the sines cancel. I'm left with theta deep is equal to the inverse sine. Now the numbers go in. There's the speed in the deep water. There's the speed in the shallow. There's the sine of the angle. Now with not enough room, so what I'm going to do is get rid of all of the other stuff there and move this thing here up to the top, and there it is. I've moved it up the top and then put the numbers in. probably should have put another stepper there, guys. Sorry about that. So this thing here goes up to the top, and then I put the numbers in. So inverse sine of, now the sine of 20 is 0.342. If I multiply that by 3.5 and then divide by 1.5, I get about 0.9ish, and that the inverse sine of that is 52.94 degrees. Sorry about my 4, it looks a bit crook. Say 53 degrees. So that's worth knowing. Now we know that the angle in the deep water is 53 degrees. We are nearly there. If I draw it out, we have deep and shallow water. There's the boundary. I'm going to draw in the normal, the right angle line. And therefore the incidence angle, the waves are coming in here at 53 degrees from the normal. I have that. And they're going to be refracted out 20 degrees from the normal on the shallow side, because if they're going to come in, if the wave comes in here, this side here will slow down, drag it round, and pull the wave round. I'll draw that. So I've drawn some waves coming in. Haven't drawn the refracted ones yet. So here we go. And then I'm going to draw in. Now they come in here, and then what happens is when they slow down, they get bent in. So they get bent. So wave comes in here, this side slows down, and this side. Oh, I've missed one. Missed one in there. Sorry, one in there. One in there. I should have drawn one in there. I beg your pardon. I messed up there. There, the waves carry on this way. Now you see they're closer together because it's going slower. They also the waves come in perpendicular to the direction of the wave. The waves don't scoot sideways. There's 53 degrees, there's 20 degrees, and they also are perpendicular, and that's 58 millimeters in the deep. There's 25 millimeters in the shallow, and I think we've done it. For those guys who struggle with that question, I hope this has been useful. Cheers, guys.